Alright, hello everybody, and today we're gonna be doing a bit of a special video. You've seen that in all of my videos. I bring out the idea in terms whether it was physics or mathematics, and then I present some examples, and some of them are challenging and some of them are easy. But today is gonna be a specialized video for applying derivatives. We're actually going to see real world actual applications, and we're gonna have a list of problems, and some will be challenging, some will be easy, some will require you just to focus because you don't need to complicate math, because when you do, you will never be able to understand it, trust me. Alright everybody, so here we have this question over here, and it says that v, which represents velocity, as a function of time is equal to t to the fourth minus 2t cubed minus 4t. It wants two things. It wants v of 1, so the velocity at time equals 1, and acceleration a at time equals 1 as well. And there's a question that I'm going to add in the end to test if you understand the idea between speed and velocity, because there's a huge difference. So pause the video and tell me if you can try this out by yourself. Okay, so the first thing that we have to solve, number one over here, is pretty simple. You can just substitute t equaling to 1. So if you do that, that's going to be 1 to the fourth. That's 1. That's 1 minus 1 to the cubed. That's 1. So 2 multiplied by that's 2 minus 4. 1 minus 2, negative 1 minus 4, so that would be equal to negative 5. Okay, and just for the sake of this question, we'll say that the units are meters per second. Alright, okay, so what about acceleration? Here you're gonna apply the derivative. Why? Because in originality, this function gives us the velocity. We want acceleration, and you already know that the position, the velocity function is nothing but the derivative of the position time. So in order to get the acceleration, you just have to differentiate again. Okay, which also reminds you of our last video, the second derivative, which that means that acceleration is nothing but the second derivative of position. So let me write it in all notations. So that means that a effective time is equal to what? Yes, the first derivative of velocity, which is also equal to what? The second derivative x double prime of position. Keep this in your mind, alright? Keep this in your mind. So let us differentiate this real quick over here. So we're going to say that d v with respect to time, well, that's equal to acceleration with respect to time, which is equal to d dt with respect to time of this, of the velocity equation. So t to the fourth, right, t to the fourth minus 2t cubed minus 4t. So we can solve this pretty quickly. You just take the difference rule in here. So that would be the derivative of t to the fourth minus derivative of 2t cubed minus derivative of 4t. So derivative of t to the fourth, use the power rule. So yeah, the power rule. So that's going to be 4t cubed, right? Minus, take the constant out, 2, multiply it by the derivative, and then take the 3 down, the power, minus 1, so that would be equal to 2 multiplied by 3, so that would be 6t, minus derivative of this constant is equal to 1, and then you multiply it by 4, so that's equal to 4. So if you want the acceleration at time equals 1, well, here is your acceleration equation. You just apply when t is equal to 1. And then you get the acceleration at time equaling 1 second. So if you solve this, actually, we have the equation for acceleration, and we got it from differentiating velocity. And it's 4t cubed minus 6t minus 4. So you plug in the numbers, you know, you get negative 6 meters per second squared. So, or unit per second squared. But for the sake of this question, let's say meters. Now, my question was, here's my special question. I want you, if you can plot it, that would be pretty cool. At time equals 1 seconds, can you tell me whether the car is speeding up? Let's say it's a car or an object. Let's say this object. At time equals 1 seconds, is it speeding up? See, I'm saying speeding. I never mentioned velocity, okay? Is it speeding up, slowing down, or neither? Pause the video and take your time. I'd encourage you if you can plot it, that would be really cool. Alright, I'm assuming you gave it a shot. So look, in order to think about speed, the way that we can define speed from velocity is that it is nothing but the absolute value of your velocity vector. So let's say that velocity is negative. Well, then your speed would be positive. Get it? Because it's a scalar quantity. Okay, it doesn't have a direction. Speed is a scalar quantity. Because your velocity can be negative in the negative direction. In the backward direction, let's say we're talking about 1 dimension, not 2 dimensions. In the backward direction, that would be negative. So you would actually be speeding up, which means that at time equals 1 second, you're speeding up. Why? Because your velocity got more negative. Because you notice here that at the velocity at time equals 1, it was -5, which means before that it must have been less negative. It must have been greater. And we said that speed is the absolute value of velocity, which means that, let's say at time equals ½ seconds, it was let's say -2 and something. What is greater, the absolute value of -2 or the absolute value of -5? Obviously, the absolute value of -5. So your answer here would be that as time goes on, unless it does have acceleration, as time goes on, this car is actually speeding up, not slowing down. Okay, everybody, so on to our next question. So this question here involves another application in real life. The equation of the function w with respect to time that you see here describes the water level of a pool being filled. And the units are in centimeters for the level that is being raised in terms of the height, and the time is in terms of seconds. So we want the instantaneous rate of change of the pool's water level after 100 seconds. Pause the video and see what you have. Alright, so it said that it wanted the instantaneous rate of change. Well, that is nothing but the derivative. So first of all, let us differentiate this function with respect to time. So we are going to see here that dw d time, or the derivative of w with respect to time, is equal to d derivative with respect to t time of this beautiful function. It has some few tweaks, but let's get through again. So we're going to use the sum rule. So we're going to take the derivative of the first part plus the derivative of the second part. So 4 root of t plus d dt of natural log of t plus 1. Pay close attention, okay? That's natural log t plus 1. Okay, so derivative of the first one, you will take the constant, multiply it by derivative. In this case, it's equal to, let's put a huge bracket for each derivative, so that's 4 multiplied by the derivative of square root of t. So let's do that on a side so we don't get confused. So dt 1 of the root of t. Well, I'll tell you what, we can actually do this using the power rule. How? Tell you what, we can rewrite the square root of t as this, buddy. Hold on. We can rewrite it as t to the half power, right? If you don't understand why, it's basically the rule for every possible root. and I actually solved a question like this before in my early calculus videos. You should go watch it. So this is some simple power rule. You take the half down, multiply it, and then you withdraw 1 from the power. So that would be half multiplied by t. So that would be t to the negative half over 2. You bring it down with a positive power and you put it under the root. So that would be equal to 1 over 2 root of t. Alright, so that is the derivative with respect to t of the root of t. 1 over 2 root t. So let's just actually erase this. So if we multiply 4 by 1 over 2 root of t, well, that would be nothing but 4 over root 2. Over 2 root t. See? Yeah, confused. Actually, we can simplify this as well. 4 over 2, that's 2. So that would be 2. Hold on. 4 over 2, we can rewrite this as 4 over 2 multiplied by 1 over root t. So that would be 2 over root t. Just to simplify even more there. Now all of that plus the derivative with respect to time of this guy over here. The natural log of t plus 1. Obviously, here we are going to apply the chain rule. So the derivative of the outer function with respect to the inner one multiplied by the derivative of the inner function. What is the derivative of the outer function? ln of x. ln of t, sorry, ln of t. What is the derivative of ln of t? That is 1 over t. So instead of 1 over t, 1 over the inner function. So 1 over t plus 1. Put a huge bracket, and then you multiply it by the inner function. Sorry, multiply by the derivative of the inner function, sorry. So derivative of t plus 1, derivative of a constant is 0, so you take that one out. So derivative of t, well, that is 1. So you multiply it by 1, and that just gives you the same answer over here, right? Okay. So now we have our full answer, kind of, for the derivative. You can plug in the numbers if you'd like, and you can also multiply them. So hang on. We can actually just plug in the numbers straight off, but let's see what we can do here. We can multiply this by this in order to sum up the fractions. So multiply denominator by denominator. So root of t multiplied by t, and then root of t multiplied by 1. Okay, sorry about that. Okay, so here we go. Root of t multiplied by t. Well, that would just be t times root of t. Okay, plus root of t. Okay. Anyways, guys, as I was saying, so you multiply the denominator by the denominator, and then you take a cross here. So that would be 2t plus 2 plus root of t. And I know it looks sophisticated, but this is what you get if you'd like to actually multiply them. But now that we have our derivative, let us actually apply and get the instantaneous rate of change, the derivative of the pool's water level after 100 seconds. So all what you do is just put 100 for each t. Alright guys, so if you approximately solve it, you're gonna get around, well, let me write it somewhere. So if you approximately solve it, w prime of 100, you're gonna get approximately, sorry, that doesn't look approximately, kind of, around, hold on, let me check, yeah, 0.20999, which is let's say 0.21, and we said the units centimeters per second. Alright everybody, and now for our last question. So this question is going to be a bit, well, not intense, but it's a really important question. Really, really important. And it has many different ways to solve it. So guys, I know I have a way to solve it because I know people in the comment section will tell me, why didn't you solve it this way? Guys, I am all open. I'm open to all ideas, and I would love to hear all ideas on how to solve this question. There are many rules. Anyways, it says over here that y is equal to the derivative with respect to x of the cubic root of x. Actually, no, wait. Alright, everybody, sorry about that. So I actually wrote the question wrong in the first place, but for whoever wants to solve the first question, which I wrote incorrectly, I mean, you can try, but here's the correct question. So it says over here that the curve y is equal to the cubic root of x, all of that raised to the power of x. Yes, this is an actual question, and it is very solvable. Now, I really want you to try your best, because if you do get this right, this question is really awesome. Okay. So we want to get the derivative of y with respect to x. Pretty simple. Let's differentiate. And we also want to evaluate it at x equals 1. Okay, remember, at x equals 1, we want to evaluate this derivative. So we want to get dy dx. Well, that would just be equal to the derivative with respect to x of this whole shenanigan. The cubic root of x, all of that raised to the xth power. So I can solve this using the chain rule. The derivative of the outer function with respect to the inner one multiplied by the derivative of the inner function. Obviously, all of that equals the derivative of the outer function, which is, well, I'm just gonna write it. Okay, I don't really have to give it a name. So the derivative of x to the x, that's the outer function, right? You're with me? With respect, well, to the inner one, the cubic root of x, all right? Multiplied by the derivative of the inner function, which is cubic root of x, all of that, obviously with respect to x. So this is basically our answer. If we get this and we evaluate at x equals 1, we can finish the video. So let us get each derivative so we don't get confused. So let's start with this guy. Derivative of x with the derivative of x to the x. Alright. So let's get that real quick. This one is a roll, and if you guys want me to make a proof video for it, I will tell you. But for now, let me tell you the following equation. Just so you know, it is a formula. So the derivative with respect to x of x to the x, well, that is equal to x to the x multiplied by the natural log of x plus x to the x. Now, yes, this is possible. This is actually possible. You can get this by doing some implicit differentiation, which I viewed over some of my questions in the last video of second derivative. So that is the first derivative that we have, okay, of the outer function. Okay, now let's get the derivative of the inner function. So d, you know, let's pick a different color. I like to be a color man. So we want to get dx with respect to x, 1 of the cubic root of x. Well, that will just be equal to the derivative with respect to x. Yes, like we did with the root of t. Remember last question. Of x to the third. Okay, where 1, remember, is n, is the power of this guy, and 3 is the base of the root, is m. Well, this is a simple power rule, so we can bring the power down and multiply it by x to the n minus 1. So that would be third multiplied by x to the third minus 1, negative third. So negative third goes down, and you're left with 1 in the numerator over 3. Sorry, that's not 3, that's a tomato. Multiplied by x to the 2/3, so that would be the cubic root, the cubic root of x squared, alright? That would be equal to the cubic root of x squared. So now we have both what we need to solve this question. We just have to apply in order to get this. And again, let's go with a different color. So yeah, what are you gonna do? Exactly. Let's go with kind of dark blue. Let's go with purple, kind of purple. So the derivative x to the x, we've already said that x to the x, and bear with me, alright? Listen, this notation makes sense, it's possible, okay? And if you guys have any other ways to solve this question, like I said, just tell me. So x to the x, and then replace each x because with respect to the inner function. So that would be the cubic root, sorry, of x, well, raised to the power of the cubic root of x, alright, multiplied by the natural log of the cubic root of x, yes, once again, plus the cubic root of x, raised to the power of cubic root of x. That's just this part, alright? That represents this part, the derivative of the outer function with respect to the inner one. Derivative of x dx with respect to cubic root of x. And if you multiply the derivative of cubic root of x, well, you have one in the numerator and this in the denominator. So 1 multiplied by this, that would be 1, that would be this in the numerator, and we would have this in the denominator, this. So our final answer for this derivative would be equal to this whole shenanigan. We don't have to write it. We just divide all of that over 3 multiplied by the cubic root of x squared. And yes, this is a legitimate logical answer that you can write in an exam and you would get a full mark. Now we just have to evaluate it at x equals 1. So let's solve it real quick. Okay guys, if you solve it, you should get an answer 0.033. Well then that means over here that finally y prime of 1, you should get approximately third, which means that this is a positive slope. This is a positive derivative. It's not steep. Tangent line is not steep there. I really hope you guys enjoyed this video. I'm going to be trying to posting more frequently, more often. I'm going to post some physics videos, mathematics, but just stay tuned, and thanks for all the support, and see you guys in a different video.